Time slows down in space, not as a metaphor, not as a poetic description of how long missions feel, not as a philosophical observation about the subjective experience of isolation. In a precise, measurable, experimentally confirmed physical sense, time itself passes at a different rate depending on where you are and how fast you are moving. A clock on the International Space Station runs at a different rate than a clock on Earth. A clock deeper in Earth's gravitational field runs slower than a clock at a higher altitude. A clock moving at high velocity runs slower than a clock at rest. These effects are small under the conditions of everyday human experience, small enough that we do not notice them, small enough that for most of human history we had no instruments sensitive enough to measure them. But they are real. They have been measured directly. They are not theoretical abstractions. They are incorporated into the GPS satellites orbiting above you right now. Because without correcting for them, the GPS system would accumulate errors of kilometers per day, making it useless. And they are not small in other contexts. Near a black hole, time dilation becomes so extreme that an observer falling toward the event horizon would appear to a distant observer to freeze in place, slowing asymptotically toward a stop, never quite crossing the horizon, suspended forever in the distorted geometry of space-time. For the observer themselves, the experience is different. They cross the horizon in finite time by their own clock, falling into a region of space-time from which no information can escape. For a hypothetical astronaut traveling at a significant fraction of the speed of light on a journey to another star, years might pass aboard the spacecraft, while decades or centuries pass on Earth. The crew would return younger than the people they left behind, not because of any biological trick or chemical intervention, because time itself passed differently for them. Tonight, we're going to examine this reality in full, not through analogy or simplification, but through the actual physics as it is understood. What does it mean that time is not absolute? What are the two distinct mechanisms that cause time dilation, velocity and gravity, and how do they work? What do the experiments confirm? And what does it mean concretely for the human experience of space travel at the scales that matter? Before we begin, if you put this on because the night is long and you need something to settle into, stay. The physics of time is among the most genuinely strange things science has ever established as true about reality. It deserves attention. Let us start with the most fundamental question. What does it mean to say that time passes at different rates in different places? For most of human history, time was assumed to be absolute. This assumption is so deeply embedded in everyday experience that it feels like a logical necessity rather than a contingent fact about the universe. A second is a second. A minute is a minute. Whether you are moving or stationary, whether you are at sea level or on a mountain, whether you are near a massive object or far from one, time was assumed to flow at the same rate for everyone, everywhere. This assumption is wrong. It was first definitively challenged by Albert Einstein in 1905 with his special theory of relativity, and extended in 1915 with his general theory of relativity. The core insight of special relativity is that the laws of physics are the same for all observers in uniform motion, and that this requires the speed of light to be constant for all observers regardless of their relative velocity. The core insight of general relativity is that gravity is not a force in the Newtonian sense, but a curvature of space-time caused by the presence of mass and energy. Both of these insights lead to the same conclusion through different routes. Time is not absolute. The rate at which time passes depends on the observer's velocity and on the strength of the gravitational field at their location. Let us be precise about what this means before we discuss the mechanisms. When physicists say time passes at different rates, they mean something measurable and concrete. Take two identical clocks designed to keep time with the highest possible accuracy, perhaps atomic clocks based on the oscillation frequency of cesium atoms. Place one clock in a specific situation, moving at high velocity or deep in a gravitational well. Keep the other clock in a reference situation, stationary relative to your frame of reference, or at a higher altitude in a weaker gravitational field. Bring them back together and compare their readings. The clocks will show different times. Not because of any mechanical imperfection, both were manufactured identically and run perfectly, but because time itself passed at different rates for the two clocks. The one in the more time-dilating situation accumulated fewer seconds, minutes, hours than the one in the less time-dilating situation. This has been measured directly, many times, with increasingly precise instruments. It is not debated in the scientific community. It is as firmly established as any fact in physics. Let us now talk about the first mechanism for time dilation, velocity. This is the effect described by special relativity, and it arises from a remarkable feature of how the universe is structured. Special relativity begins with two postulates. First, the laws of physics are identical for all observers in uniform motion, moving at constant velocity without acceleration. There is no experiment you can perform that will distinguish being at rest from moving at constant velocity. Motion is relative. There is no absolute rest frame in the universe. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the source of the light. The second postulate is the extraordinary one. It contradicts common intuition about how velocities add. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the sum of the train's speed and the throwing speed. This is Galilean velocity addition, and it works perfectly for everyday objects. But light does not obey this rule. If you shine a flashlight forward from a moving spacecraft, the light moves away from you at exactly c, approximately 299,792 kilometers per second. And a stationary observer on the ground also measures the light moving at exactly c. Not c plus the spacecraft's velocity, just c. This seems impossible. If you and I both measure the same beam of light and both get the same speed, but we are moving relative to each other, something must give. Velocity is distance divided by time. If we get the same velocity, but we are measuring the distance the light travelled relative to our different reference frames, those distances might be different, meaning we must be measuring different times. And this is exactly what relativity requires. The resolution of the apparent impossibility is that time itself is not universal. Clocks moving relative to each other run at different rates. Distances along the direction of motion contract for moving objects. The totality of space and time, what Einstein called space-time, is a four-dimensional structure, and different observers slice through this structure differently, depending on their relative motion. The mathematical expression of time dilation from velocity is given by the Lorentz factor, the Greek letter gamma, which equals 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. For a clock moving at velocity v relative to a stationary observer, the moving clock runs slower by a factor of gamma. At low velocities, velocities much smaller than c, gamma is very close to 1, and time dilation is negligible. At velocity v equal to 10% of the speed of light, gamma is approximately 1.005. The moving clock runs about 0.5% slow. At 50% of c, gamma is approximately 1.15. The moving clock runs about 15% slow. At 90% of c, gamma is approximately 2.3. The moving clock runs at less than half speed relative to the stationary observer. At 99% of c, gamma is approximately 7.1. At 99.9% of c, gamma is approximately 22.4. As v approaches c, gamma approaches infinity. The moving clock would run infinitely slowly. Time would effectively stop for it from the perspective of a stationary observer. This is not a theoretical prediction awaiting confirmation. It is experimentally verified. Muons, elementary particles created in the upper atmosphere when cosmic rays collide with atmospheric nuclei, have a half-life of approximately 2.2 microseconds at rest. They are created at altitudes of approximately 10 to 15 kilometers and travel downward at approximately 99.7% of the speed of light. Classical physics predicts that in 2.2 microseconds they would travel only about 660 meters before half of them had decayed, nowhere near enough to reach sea level. Yet we detect them at sea level. The explanation is time dilation. Traveling at 99.7% of the speed of light, they experience time at approximately 1/14 the rate of a stationary observer. What is 2.2 microseconds in their frame is about 31 microseconds in the Earth's frame, enough time to travel the full 15 kilometers and reach detectors on the ground. This was one of the first experimental confirmations of special relativity, and it has been reproduced countless times with increasingly precise measurements. The muons serve as natural moving clocks, whose slowing is directly observable through their survival rate at sea level. Let us now talk about the second mechanism, gravitational time dilation. This is the effect described by general relativity, and it arises from an even more profound insight about the nature of space-time. General relativity emerged from Einstein's attempt to reconcile special relativity with gravity. The starting point is what Einstein called the equivalence principle, the observation that being in a gravitational field is locally indistinguishable from being in an accelerating reference frame. An observer in a closed box on Earth's surface cannot tell through any local experiment whether they are stationary in Earth's gravity or accelerating upward in free space at 9.8 meters per second squared. The effects are identical. This equivalence between gravity and acceleration has a profound consequence for light and time. Consider a thought experiment. A beam of light is emitted from the floor of an accelerating rocket toward the ceiling. By the time the light reaches the ceiling, the rocket has accelerated. The ceiling is now moving faster than it was when the light was emitted. An observer on the ceiling measures the light as slightly redshifted. Its frequency is lower than when it was emitted. This is the Doppler effect applied to an accelerating system. But by the equivalence principle, the same thing must happen in a gravitational field. Light climbing out of a gravitational well, moving from a region of stronger gravity to weaker gravity, must be redshifted. This is gravitational redshift, and it implies that time must run slower in stronger gravitational fields. Here is why. If the frequency of light is lower by the time it climbs out of the gravitational well, that means fewer oscillations per second are arriving at the higher altitude, compared to what was emitted per second at the lower altitude. For frequency to be lower at the top than at the bottom, time must be running faster at the top. Clocks tick faster where gravity is weaker. The mathematical expression of gravitational time dilation involves the gravitational potential, the energy required to move a unit mass from a given location to infinity. Clocks at lower gravitational potential, deeper in a gravitational well, closer to a massive object, run slower than clocks at higher gravitational potential, farther from the massive object. At the surface of Earth, the difference in gravitational potential between sea level and a height of 1 kilometre is small, corresponding to a time dilation factor of approximately 1 plus 1.09 times 10 to the minus 13. This means a clock at 1 kilometre altitude gains approximately 1.09 times 10 to the minus 13 seconds per second compared to a clock at sea level, about 9.4 nanoseconds per day. Tiny, but measurable. The Pound-Rebka experiment, performed at Harvard University in 1959, was the first direct measurement of gravitational redshift. A gamma ray was emitted from the bottom of a 22.6 metre tower and detected at the top. The expected gravitational redshift over this 22.6 metre height difference was approximately 2.46 times 10 to the minus 15, an almost unimaginably small shift. Yet using the Mossbauer effect, which provides extremely precise measurement of gamma ray frequencies, the experiment measured a shift of 2.57 plus or minus 0.26 times 10 to the minus 15, consistent with the prediction of general relativity. This experiment was a landmark in experimental physics. It confirmed that gravity affects the flow of time at the level of a 22-metre height difference in a Harvard building. Let us now talk about the GPS system, the most familiar practical consequence of relativistic time dilation, and the clearest demonstration that this is not abstract theory, but engineering reality. GPS satellites orbit Earth at an altitude of approximately 20,200 kilometers. At this altitude, two competing relativistic effects operate simultaneously. The first effect is gravitational. GPS satellites are 20,200 kilometers above Earth's surface. They are at a higher gravitational potential than clocks on the ground. Higher gravitational potential means faster clock rate. GPS satellite clocks therefore run faster than ground clocks due to this gravitational effect, by approximately 45.9 microseconds per day. The second effect is velocity-based. GPS satellites orbit Earth at approximately 3.87 kilometers per second. This velocity causes special relativistic time dilation. Velocity slows clocks. GPS satellite clocks therefore run slower than ground clocks due to this velocity effect, by approximately 7.2 microseconds per day. The net effect is the combination of both. The gravitational effect wins, and GPS satellite clocks run fast by approximately 45.9 minus 7.2 equals 38.7 microseconds per day, relative to clocks on the ground. 38.7 microseconds per day may seem trivial. It is not. GPS works by measuring the time it takes for signals to travel from satellites to receivers. Light travels approximately 11.4 kilometers in 38.7 microseconds. If GPS receivers did not correct for this accumulated relativistic clock error, the system would accumulate positioning errors of approximately 11.4 kilometers per day, making GPS useless for any practical navigation application within hours of operation. GPS receivers and the satellites themselves are designed with these relativistic corrections built in. The satellite clocks are manufactured to run slightly slower than they would at sea level, compensating for the relativistic speed-up that will occur once they are launched into orbit, so that once in orbit they run at the same rate as ground clocks. Without this relativistic engineering, GPS would not work. This is perhaps the most compelling everyday demonstration of the reality of relativistic time dilation. Every time you use GPS navigation, you are implicitly relying on corrections derived from general and special relativity. The physics is not optional. It is required for the technology to function. Let us now talk about what time dilation means at the scales relevant to human space travel, at the scales of missions to other planets, to nearby stars, and in the extreme environments of neutron stars and black holes. For current human spaceflight, the effects are real but small. The International Space Station orbits at approximately 400 kilometers altitude, at approximately 7.66 kilometers per second. The velocity effect, special relativistic time dilation, causes ISS clocks to run slower than Earth clocks by approximately 25.6 microseconds per day. The gravitational effect, general relativistic time dilation, causes ISS clocks to run faster than Earth clocks by approximately 0.26 microseconds per day. The velocity effect dominates, and the net result is that ISS clocks run slower than Earth clocks by approximately 25.3 microseconds per day. For a 6-month ISS mission, this accumulates to approximately 0.005 seconds, 5 milliseconds. An astronaut returning from a 6-month mission has aged approximately 5 milliseconds less than people remaining on Earth. This is measurable, but physiologically negligible. For missions to Mars, the effect is similarly small. A round trip to Mars, approximately 18 months total, at the typical trajectory velocities, would produce a time difference of perhaps 20 to 30 milliseconds. Noticeable to precise atomic clocks, imperceptible in any biological sense. The situation changes dramatically at higher velocities. This is where the Lorentz factor begins to produce genuinely significant effects on human timescales. Consider a hypothetical mission to Proxima Centauri, the nearest star system at 4.24 light-years from Earth. At current maximum spacecraft velocities, roughly 70 kilometers per second for the fastest human-made spacecraft, the journey would take approximately 18,000 years. No time dilation correction is needed because time dilation at this velocity is negligible, and neither the crew nor anyone who saw them leave would live to see them return. But consider increasingly higher velocities. At 10% of the speed of light, 30,000 kilometers per second, the journey takes 42 years by Earth clocks. By the crew's clocks, it takes approximately 41.9 years, barely different. At this velocity, the Lorentz factor is only about 1.005, still negligible in practical terms. At 50% of c, the journey takes 8.5 years by Earth clocks. By the crew's clocks, it takes approximately 7.4 years. The crew ages about 13% less than expected. Significant enough to notice over a lifetime, but not dramatic. At 90% of c, the journey takes 4.7 years by Earth clocks. By the cruise clocks, it takes approximately 2 years. The Lorentz factor is about 2.3. The crew ages 2 years, while Earth ages 4.7 years. At 99% of sea, the journey takes 4.3 years by Earth clocks. By the cruise clocks, it takes approximately 7 months. The Lorentz factor is about 7.1. The crew ages 7 months, while Earth ages 4.3 years. At 99.9% of sea, the journey takes 4.24 years by Earth clocks. By the cruise clocks, it takes approximately 2.3 months. The Lorentz factor is about 22.4. The crew ages about 70 days, while Earth ages 4.24 years. These numbers illustrate the profound asymmetry that time dilation creates for interstellar travel. At high enough velocities, a crew could traverse vast distances by Earth's reckoning, while aging only modestly by their own reckoning. The cost is the disconnection. Everyone they knew ages and potentially dies, while they barely age at all. When they return, they are biologically younger than people of their same age who remained on Earth. This is not science fiction. It is the straightforward mathematical consequence of special relativity applied to hypothetical high-velocity travel. The science fiction part is the propulsion. Achieving 99% of the speed of light requires energy that no known or foreseeable technology can provide. But the time dilation itself is physics, not fantasy. Let us now talk about the extreme end of gravitational time dilation. What happens near a black hole, and what the physics actually says about the behavior of time in the most extreme gravitational environments in the universe. A black hole is a region of space-time where the curvature has become so extreme that the escape velocity exceeds the speed of light. Nothing that enters the event horizon, the boundary of the black hole, can escape. Not light, not information, not any physical influence. The event horizon of a black hole is not a physical surface. It is a mathematical surface in space-time, a boundary defined by the geometry of the gravitational field. An observer falling freely toward a black hole would not feel anything special as they cross the event horizon. There is no local physical marker, no physical barrier, no sudden change in their immediate environment. They cross a mathematical boundary with no local consequence. But what happens to time near a black hole is extraordinary. Gravitational time dilation becomes more extreme as you approach a black hole's event horizon. Consider an observer hovering at some fixed distance from the event horizon, maintaining a constant position relative to the black hole by continuous thrust of a rocket. As this observer hovers closer and closer to the horizon, their clocks run slower and slower compared to a distant observer far from the black hole. At the event horizon itself, the time dilation becomes infinite. A clock at the event horizon would appear from a distance to run at 0 rate. From the perspective of a distant observer, the hovering clock at the horizon has stopped entirely. This produces the famous apparent paradox of an infalling observer. Imagine watching an astronaut fall toward a black hole. As they approach the event horizon, their apparent motion slows. They appear to slow down relative to your distant clock. The light they emit to you is gravitationally redshifted. It shifts toward longer wavelengths, eventually to radio waves, eventually to wavelengths too long to detect. From your perspective, the astronaut appears to asymptotically approach the horizon, slowing infinitely, never quite crossing it, their image fading and reddening. From the astronaut's perspective, nothing unusual happens at the horizon. They fall through it in finite time by their own clock, The gravitational tidal forces, the difference in gravitational pull between their head and feet, may or may not be significant at the horizon, depending on the mass of the black hole. For a stellar mass black hole, the tidal forces at the horizon are enormous, and the astronaut would be spaghettified, stretched apart along the radial direction before reaching the horizon. For a supermassive black hole, millions or billions of solar masses, the tidal forces at the horizon are relatively gentle, and the astronaut could cross it without immediate physical consequence. Beyond the horizon, the astronaut is in a fundamentally different kind of region. The singularity at the center, where the curvature of space-time becomes infinite, lies in their future. In general relativistic terms, once inside the event horizon, the singularity is not somewhere in space at the center of the black hole. It is somewhere in time, in the astronaut's future. They cannot avoid it any more than they can avoid tomorrow. The interior of a black hole has a different causal structure than the exterior. All time-like paths inside the horizon lead to the singularity. The time dilation near a black hole has been beautifully illustrated by the film Interstellar, whose science consultant was the Nobel Prize-winning physicist Kip Thorne. In the film, the crew lands on a planet near a supermassive black hole and spends approximately 1 hour on its surface, during which time 23 years pass on Earth. This corresponds to an extraordinary time dilation factor. The physics is qualitatively correct. Massive time dilation near the event horizon of a massive black hole is exactly what general relativity predicts. The specific numbers depend on exactly how close to the horizon the planet is assumed to orbit. Let us now talk about what experimental physics has confirmed about time dilation, beyond the experiments already mentioned, about the direct measurements that have verified both types of time dilation with increasing precision. The most famous direct test of velocity-based time dilation beyond the muon experiment was performed in 1971 by Joseph Haffel and Richard Keating. They flew 4 cesium atomic clocks around the world in commercial airplanes, once eastward and once westward, and compared the elapsed time on the flying clocks with the elapsed time on reference atomic clocks at the United States Naval Observatory. The flying clocks experience both velocity-based and gravitational time dilation. Flying eastward with Earth's rotation, they move faster relative to the non-rotating geocentric frame, and therefore slow down more from velocity effects. Flying westward against rotation, they move slower. The gravity effect acts in the opposite direction from the velocity effect. Higher altitude means faster clocks. The predictions of special and general relativity were specific and different for the eastward and westward flights. The eastward flying clocks were predicted to lose approximately 40 nanoseconds relative to ground clocks from the net effect. The westward flying clocks were predicted to gain approximately 275 nanoseconds. The measured values were eastward, minus 59 plus or minus 10 nanoseconds. Westward, plus 273 plus or minus 7 nanoseconds. The agreement with the relativistic predictions, calculated from the actual flight paths and altitudes, was within experimental uncertainty. The experiment was a direct confirmation of relativistic time dilation using commercial airplane flights. More recent experiments using optical atomic clocks, the most precise timekeeping devices ever constructed, have confirmed relativistic time dilation with extraordinary precision. In 2010, researchers at NIST demonstrated that an optical lattice clock could detect the gravitational time dilation between altitudes differing by only 33 centimeters, 1 foot. The clock at the higher altitude ran fast, by approximately 4 times 10 to the minus 17 seconds per second, a difference of 400 quadrillionths. The agreement with general relativity was at the percent level. This measurement is remarkable for a specific reason. A height difference of 33 centimeters produces a measurable time dilation. The difference in time rate between your head and your feet is measurable with current atomic clocks. Time literally flows at different rates at different heights in Earth's gravitational field, and we can now measure the difference across distances comparable to the length of your arm. Let us now talk about the twin paradox, one of the most famous and most frequently misunderstood thought experiments in the history of physics, which gets at something fundamental about what time dilation means. The twin paradox goes as follows. Suppose identical twins are born on Earth. One twin, call them the traveller, boards a spacecraft and travels to a distant star at very high velocity. The other twin, the stay-at-home, remains on Earth. When the traveller returns, they are younger than the stay-at-home twin. More time passed for the stay-at-home twin than for the traveller. This much is straightforward from what we have already discussed. The paradox arises from a naive application of the relativity of motion. Special relativity says that all motion is relative. From the traveller's perspective, it is the Earth that moves away, while they remain stationary. Should not the traveller observe the earthbound twin aging more slowly, since from the traveller's frame of reference the earthbound twin is moving? If the situation were perfectly symmetric, both twins moving at constant velocity relative to each other for the entire experiment, there would indeed be a symmetric situation and no age difference at the reunion. But the situation is not symmetric. The traveller must decelerate, stop, and accelerate back toward Earth. This acceleration breaks the symmetry. The traveller is not always in a single inertial frame. They shift from one inertial frame to another during the turnaround. The stay-at-home twin remains in a single inertial frame throughout. The resolution of the twin paradox is that the asymmetry comes from the acceleration of the traveller during the turnaround. The traveller's path through space-time is genuinely different from the stay-at-home twin's path, and the path length through space-time, the proper time, is genuinely shorter for the traveller. When they reunite, the traveller is genuinely younger. Both observers agree on this. There is no paradox, only an apparent symmetry that is broken by the real asymmetry of their trajectories through space-time. General relativity provides a way to understand this more completely. The traveller during their acceleration phases is equivalent to being in a gravitational field by the equivalence principle. During the deceleration and re-acceleration phases, the traveller experiences what is equivalent to a strong gravitational field, oriented in specific directions. If you carefully apply general relativity to compute the time that passes in the accelerating phases, including the turnaround, the asymmetry resolves completely, and the predicted age difference is the same as the special relativistic calculation. The twin paradox is not a paradox. It is a thought experiment that reveals something profound about the structure of space-time, that the elapsed time along a path through space-time depends on the shape of the path, not just the endpoints. Let us now talk about the concept of space-time intervals, the mathematical structure that underlies all of relativistic time dilation and makes it coherent rather than paradoxical. In ordinary three-dimensional space, the distance between 2 points is given by the Pythagorean theorem, the square root of the sum of the squares of the differences in x, y, and z coordinates. This distance is the same for all observers, regardless of their orientation or position. In special relativity, space and time are united into four-dimensional space-time, and the relevant quantity is the space-time interval, a generalization of the spatial distance concept. The space-time interval squared equals c squared times the time difference squared minus the spatial distance squared, or equivalently minus c squared times the time difference squared plus the spatial distance squared, depending on the sign convention chosen. The key property of the space-time interval is that it is invariant. It has the same value for all inertial observers, regardless of their velocity. Different observers may disagree about the time difference and the spatial distance separately. This is where the relativity of simultaneity and length contraction enter. But they all agree on the space-time interval computed from their different measurements. The space-time interval can be positive, negative, or zero. When it is positive, in the convention where time contributes positively, the two events are separated by what is called a time-like interval. They are in each other's causal past or future. A clock, moving from one event to the other, measures the proper time between them, the square root of the space-time interval divided by c squared. This proper time is what the clock actually reads. It is shorter for any path other than the straight line path, which is why moving clocks always run slow compared to stationary ones. When the space-time interval is negative, the events are separated by a space-like interval. They cannot be causally connected. No clock can travel between them because doing so would require faster-than-light travel. Different observers may disagree about the order of space-like separated events. There is no invariant notion of which happened first for such events. When the space-time interval is exactly zero, the events are connected by a light signal. Light travels between them. From the perspective of a photon, if a photon could have a perspective, the space-time interval along its path is always zero. It reaches its destination in zero proper time. Photons do not experience time. This is not a metaphor or a loose statement. The proper time along a photon's world line in space-time is identically zero. This mathematical structure, the invariance of the space-time interval and its relationship to proper time, is the foundation of everything we have discussed. Time dilation is not an illusion or a measurement artifact. It is a real consequence of the geometry of space-time. The actual elapsed time along different paths through space-time depends on the shape of those paths. Let us now talk about what this means physically, about what it means experientially for a person undergoing significant time dilation. For the traveller moving at high velocity or deep in a gravitational field, nothing feels unusual. Their heartbeat is normal, their thinking is normal. Biochemical reactions in their body proceed at normal rates relative to their own clocks. Food digests normally. They age normally relative to their own experience. They feel no stretching or slowing. The time dilation is not experienced as anything because it is their time that defines their experience. What they notice, if they are paying attention, is that the outside universe behaves unusually. A traveller at 99.9% of the speed of light toward a star 4.24 light-years away would arrive in about 70 days by their clock. But looking ahead, they would see the star approaching. The distance contracts in the direction of motion. The star that was 4.24 light-years away is now Lorentz contracted to about 0.19 light-years in the traveller's frame. They travel 0.19 light-years at nearly the speed of light, and it takes about 70 days. Perfectly consistent. But the universe they departed from, Earth, the solar system, is aging rapidly in their frame during the return journey. If they look back during the turnaround and acceleration phases, the Earth clock runs very fast, appearing to jump forward by years in the time the traveller takes to turn around. This directional asymmetry, their own experience unchanged, the universe's time appearing compressed in their direction of travel, is the strange but logically consistent structure of relativistic motion. For someone near a black hole, the experience is similarly local normal. Sitting on a platform hovering near the event horizon, everything in the immediate environment is normal. Their clock ticks normally, their heartbeat is normal, biochemistry is normal. But looking up toward the distant universe, they would see everything speeded up enormously. Stars moving fast, processes that take years completing in seconds, the universe appearing to age rapidly. And the distant universe looking at them would see them nearly frozen, almost stationary, their signals arriving with enormous gravitational redshift at very low frequency. Let us now talk about what these effects imply for the most extreme known environments in the universe, neutron stars, which represent a more accessible laboratory for gravitational time dilation than black holes. Neutron stars are the collapsed cores of massive stars that have undergone supernova explosions. They are extraordinarily compact. A typical neutron star has a mass of about 1.4 solar masses, compressed into a sphere of about 10 kilometers radius. For comparison, the Sun's radius is about 696,000 kilometers. A neutron star is about 70,000 times smaller than the Sun, but contains about 1.4 times as much mass. This extraordinary density creates an intense gravitational field. The gravitational time dilation on the surface of a neutron star is significant by any measure. A clock on the surface of a neutron star runs at approximately 70 to 80% of the rate of a distant clock, depending on the specific mass and radius of the neutron star. A second on the surface of a neutron star corresponds to approximately 1.2 to 1.4 seconds for a distant observer. Neutron stars are observable. They emit radiation at various wavelengths, and many are detected as pulsars, rotating neutron stars that emit beams of radio waves. The timing properties of pulsars, their precise rotation rates, and how those rates change over time, allow extremely precise tests of general relativity in strong gravitational fields. The Hulse-Taylor binary pulsar, a system of two neutron stars orbiting each other, discovered in 1974, provided the first indirect evidence for gravitational waves and a precise test of general relativistic effects, including gravitational time dilation. The orbital dynamics of the system are affected by gravitational time dilation in ways that general relativity predicts with extraordinary precision. The agreement between observation and prediction over decades of monitoring has been at the level of better than 0.1%. Let us now talk about a specific and underappreciated aspect of time dilation, its connection to the arrow of time and to the deep question of why time seems to flow in one direction. In physics, the fundamental equations, both Newton's laws and the equations of special and general relativity, are time symmetric. They work equally well in both time directions. A film of a ball bouncing runs as well forward as backward from the perspective of Newton's laws. Yet our experience of time is profoundly asymmetric. The past is fixed, the future is open. Entropy increases. We remember yesterday, but not tomorrow. Time dilation does not resolve this asymmetry, but it relates to it in interesting ways. The proper time along a world line in space-time is the time experienced by the clock or observer following that world line. It is a local, observer-dependent quantity. The arrow of time, why entropy increases, is a global statistical property of systems with many degrees of freedom. What relativity adds to our understanding of time's asymmetry is the distinction between the past light cone and the future light cone of any event, the set of events that could have causally influenced the present versus the set that could be causally influenced from the present. This causal structure, defined by the invariant speed of light, is an objective feature of spacetime, independent of any observer's velocity. It distinguishes the past from the future in a frame-independent way. The subjective experience of time flowing, the now, the moving present, is not directly addressed by physics. Physics describes the geometry of space-time and the distribution of matter and energy within it, but does not directly account for why we experience the universe as a sequence of presents rather than as a static, four-dimensional block. This remains one of the deepest open questions at the boundary of physics and philosophy of mind. What is clear from relativity is that the present is not universal. There is no frame-independent notion of now across distant locations. Events that are simultaneous in one reference frame are not simultaneous in another. The special relativity of simultaneity means that the present moment is observer-dependent for spatially separated events in a way that has no classical analogue. Two observers passing each other at high speed would disagree about which events on a distant star are happening now. This relativity of simultaneity is not merely theoretical, it is a consequence of the same mathematics that produces time dilation and has been confirmed by the same experiments. It implies that the universe at large is better described as a four-dimensional block, all events at all times existing in an eternal geometric structure, than as a three-dimensional space with a universal present moment evolving through time. This is a strange picture. It is the picture that follows from taking the mathematics of relativity seriously as a description of reality rather than as a calculational tool. And it is the picture within which time dilation makes most natural sense, as the consequence of different observers tracing different paths through a static four-dimensional structure, accumulating different amounts of proper time along their different trajectories. Let us now talk about what current research is exploring at the boundaries of what we understand about time, about the open questions where the physics of time meets quantum mechanics, and where our understanding becomes genuinely uncertain. General relativity and quantum mechanics are the two most successful physical theories ever developed. Both have been confirmed to extraordinary precision in their respective domains. They are also fundamentally incompatible at a mathematical level. The smooth, curved space-time of general relativity is inconsistent with the probabilistic, quantized nature of quantum mechanics when both are relevant simultaneously. This incompatibility becomes physically relevant in situations of extreme density and curvature, at the center of black holes and at the moment of the Big Bang, where quantum effects and gravitational effects are simultaneously important. A complete theory of quantum gravity, one that encompasses both general relativity and quantum mechanics, would describe physics in these extreme regimes. The leading candidates for a theory of quantum gravity include string theory and loop quantum gravity, among others. Both propose that the smooth continuous spacetime of general relativity is an approximation, that at very small scales, near the Planck length of approximately 10 to the minus 35 meters, spacetime has a discrete, granular structure rather than a continuous, smooth structure. If this is correct, time itself may be discrete at the Planck scale. There may be a minimum time interval, the Planck time, of approximately 5 times 10 to the minus 44 seconds, below which the concept of time has no meaning. The smooth flow of time that we experience, even the smooth time dilation of general relativity, would be an emergent phenomenon arising from the averaging over vast numbers of discrete space-time quanta. What does this mean for time dilation? At the scales where relativistic time dilation has been measured, from nanoseconds to years, over distances from centimeters to thousands of kilometers, the discrete nature of space-time at the Planck scale is completely irrelevant. The predictions of general and special relativity are essentially exact in these regimes. But near the singularity of a black hole, or at the beginning of the universe, our current theories break down, and the correct physics requires a theory we do not yet have. Let us talk about what the physics of time dilation means for the specific human experience of long-duration space missions. Not the abstract mathematical framework, but the concrete experiential reality of what it would mean to be a person subject to significant relativistic effects. Consider the most realistic near-term scenario for significant time dilation: a crewed mission to Mars. The velocities involved produce time dilation effects of only milliseconds over the entire mission. These are real, measurable, and incorporated into the timekeeping systems aboard the spacecraft. But for the crew, they are imperceptible. Their experience of time is indistinguishable from what it would be on Earth. They age at the same rate they would have aged had they stayed home. The difference is less than a heartbeat across the entire mission. Now consider a more speculative scenario, a mission using a hypothetical propulsion system capable of accelerating a spacecraft at one standard gravity continuously, a constant 1g acceleration. The same gravitational pull you feel standing on Earth would provide comfortable artificial gravity for the crew while achieving relativistic velocities within timescales of months to years. This is the most commonly cited physically plausible scenario for genuinely relativistic human spaceflight, even though the propulsion technology required is far beyond anything currently conceivable. Under constant 1g acceleration, the spacecraft reaches approximately 77% of the speed of light after 1 year of proper time, 1 year as experienced by the crew. After 1 year of acceleration, you decelerate for 1 year to stop at the destination. For the round trip, you accelerate for 1 year, decelerate for 1 year, accelerate back for 1 year, decelerate for 1 year. 4 years of proper time for the crew. The distance covered in this 4-year subjective trip is approximately 7 light-years by Earth's reckoning, enough to reach several of the nearest star systems. The asymmetry becomes dramatic for longer missions under this same 1g constant acceleration. Accelerating for 5 years subjective time, then decelerating for 5 years, a 10-year one-way journey as experienced by the crew, you would reach distances of approximately 250 light-years from Earth. The crew ages 10 years. Earth ages approximately 253 years. Accelerating for 10 years and decelerating for 10 years, a 20-year one-way subjective journey, you would reach approximately 24,000 light-years from Earth, almost a quarter of the way across the Milky Way galaxy. The crew ages 20 years. Earth ages approximately 24,000 years. These are the numbers that make the twin paradox concrete. Not a thought experiment, but a physical reality, if the propulsion existed. The crew of such a mission would return to an Earth that had aged thousands of years, while they had aged decades. The civilization that sent them would be unrecognizable. Everyone they had known would be long dead. Languages would have changed. Political structures would be unrecognizable. The technology would be incomprehensible. They would return as strangers to a world that had forgotten them, if it remembered them at all. This is the terrifying human reality of significant time dilation. Not the physics itself. The physics is elegant and internally consistent, but the human experience of it, the severing of connection, the return to a world that has moved on without you, the isolation not just in space, but in time. Let us talk now about the psychological dimension of this severing, about what it would mean for human beings to experience a significant disconnect between their subjective time and the world's time. Human psychology is deeply structured around temporal continuity. Our sense of identity is built on memory, on the continuous narrative connecting who we were to who we are to who we will be. Our relationships are built on shared time, on the accumulation of experience with specific other people who are aging alongside us. Our sense of belonging to a community, a family, a culture, a civilization, depends on participating in the same temporal flow as that community. Significant time dilation severs these connections in a fundamental way. A crew travelling at high velocity ages at one rate, while everyone they love ages at a different rate. Letters sent during the mission arrive with a time lag corresponding to the light travel time, and the senders age rapidly between sending and receiving a reply. By the time a reply arrives from Earth, the correspondent who sent the original message may have aged years. The relationship exists in a kind of temporal asynchrony that has no precedent in human experience. The psychological research on long-duration isolation missions, Antarctic winter rovers, submarine deployments, simulated Mars missions, reveals consistent patterns of psychological challenge. The third quarter phenomenon, increased psychological stress in the second half of a mission, appears reliably across different mission types and durations. Interpersonal conflict within small crews intensifies with mission length. The sense of connection to home diminishes as communication delays lengthen and as the mission context becomes increasingly divorced from everyday earthly concerns. For a genuinely relativistic mission, these effects would be amplified beyond anything in existing research. The crew would know that each week of their subjective experience corresponds to months or years of Earth time. They would know that people they love are aging and dying at an accelerated rate from their subjective perspective. They would know that the world they left is becoming unrecognizable, that if they survive and return, they will return to a future rather than a home. No psychological research has examined the effects of this specific form of temporal dislocation because it has never been experienced and cannot be experimentally simulated in any meaningful way. The closest analogies are inadequate. The isolation of long submarine deployments, the disconnection experienced by long-duration ISS astronauts. But these involve at most months of mission time, during which the world at home changes relatively little. Genuinely relativistic time dilation would involve returning to a world separated from departure by decades or centuries. Let us now talk about the specific cognitive question of how a person would experience the distorted time of relativistic travel, about whether the experience of time would feel different or would feel entirely normal. The answer from physics is clear. The experience would feel entirely normal. The crew's subjective time is defined by their proper time, the time accumulated along their world line. Their heartbeats, their thoughts, their biochemical processes all proceed at the rate set by their proper time. They do not feel slowed down because they are not slowed down relative to their own frame. They are not experiencing fewer thoughts per second. They are experiencing the same thoughts per second, but those seconds are longer by the external world's reckoning. This normality of experience is what makes relativistic time dilation so conceptually strange. There is no sensation accompanying it, no feeling of time flowing strangely, no perceptible marker distinguishing the traveller's subjective experience from a non-relativistic mission. The distortion exists only in the relationship between the traveller's proper time and the coordinate time of an external reference frame. What would be perceptible is the evidence of time dilation in the external world. If the crew has communication with Earth, even with the substantial light travel time delays, they would observe the Earthbound correspondent aging visibly faster than they are. A video message sent from Earth showing a correspondent would, over successive messages, show that correspondent aging at an accelerated apparent rate. The universe's processes, stellar evolution, decay of radioactive isotopes in samples they carry, the orbital positions of planets, would all be consistent with the external time having passed faster than their subjective time. There is also a visual effect that relativistic travellers would experience, called the relativistic aberration of light, combined with the Doppler effect, that makes the universe look distinctly different at high velocity. Starlight ahead of the traveller would be blue-shifted, appearing at higher frequencies, brighter, more energetic. Starlight behind would be red-shifted, appearing dimmer and at lower frequencies. The angular distribution of stars would be distorted. Stars would appear to cluster toward the forward direction, as if being swept ahead by the spacecraft's motion. At very high velocities, the forward hemisphere would contain most of the stars in the sky, compressed into a narrow cone, while the backward hemisphere would be nearly empty. This visual distortion is not merely an optical illusion. It reflects the real redistribution of electromagnetic energy in the traveller's reference frame. The photons hitting the forward-facing part of the spacecraft have more energy. They could cause more damage from radiation, while photons from behind have less energy. This has practical engineering implications for very high-velocity spacecraft design. Let us now talk about an aspect of time dilation that connects to current observations in astronomy, about how time dilation affects what we observe when we look at distant objects in the universe. When we observe objects at cosmological distances, galaxies and quasars billions of light years away, we are looking back in time. The light we receive left those objects billions of years ago and has been travelling to us ever since. This is the familiar light travel time effect. Not relativistic time dilation, but simply the finite speed of light. But there is genuine relativistic time dilation in cosmological observations too. The universe is expanding. Distant galaxies are receding from us at velocities that approach significant fractions of the speed of light for the most distant observable objects. This recession velocity produces relativistic redshift in the light from these objects. The light is stretched to longer wavelengths, not just by the Doppler effect, but by the expansion of space itself. Related to this is a genuine time dilation effect in cosmological observations. If we observe a class of objects at cosmological distances that have a known intrinsic time evolution, objects whose light output changes in a specific way over time, we can measure whether that evolution appears slower at high redshift than it would appear nearby. Type 1a supernovae provide exactly this test. These are explosions of white dwarf stars that have characteristic light curves. Their brightness rises and falls in a specific pattern over a specific time period. They are observed at both low and high redshift. If cosmological redshift is associated with time dilation, as the standard cosmological model predicts, then high redshift supernovae should appear to evolve more slowly than low redshift supernovae by exactly the factor predicted by their redshift. This has been measured and confirmed. High redshift supernovae do show time-dilated light curves, stretched by exactly the factor predicted by their cosmological redshift. This is direct observational evidence for cosmological time dilation, the same physical effect that causes GPS corrections and muon survival rates, now observed at cosmic distances in the light curves of exploding stars. The cosmological time dilation is not a small effect. A supernova at redshift Z equals 1, meaning its light has been shifted to twice the original wavelength, appears to evolve at half the rate of a nearby supernova. A supernova at redshift Z equals 2 appears to evolve at 1/3 the rate. These are large, clearly observable effects that have been measured with precision. Let us now talk about the relationship between time dilation and the detection of gravitational waves, one of the most recent and most significant experimental developments in the physics of space-time. Gravitational waves are ripples in the fabric of space-time, oscillating distortions of the geometry of space and time propagating at the speed of light. They were predicted by general relativity in 1916, but only directly detected for the first time on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, LIGO. The first detection was the gravitational wave signal from the merger of two black holes approximately 1.3 billion light-years away, each with masses of approximately 29 and 36 solar masses. The merger produced a final black hole of approximately 62 solar masses. The missing 3 solar masses were converted into energy emitted as gravitational waves in a fraction of a second, releasing more power than all the stars in the observable universe combined, briefly, in the form of gravitational radiation. Gravitational waves are relevant to our discussion of time dilation because they are literally oscillations of the metric of space-time. They cause time to run faster and slower alternately as the wave passes. When a gravitational wave passes through a region of space, the space-time metric oscillates. Distances in one direction stretch, while distances in the perpendicular direction compress, then vice versa, at the frequency of the wave. Clocks in the stretched direction run at slightly different rates from clocks in the compressed direction, by an amount proportional to the strain amplitude of the wave. For the first LIGO detection, the strain amplitude, the fractional change in distance, was approximately 10 to the minus 21. This means the 4-kilometer arms of LIGO changed in length by approximately 4 times 10 to the minus 18 meters during the detection, a fraction of the diameter of a proton. The corresponding time dilation effect, the fractional change in clock rate, was of the same order. LIGO works by measuring this tiny change in arm length using laser interferometry, bouncing laser light back and forth in the two arms and measuring the interference pattern. When a gravitational wave passes, the interference pattern shifts by an amount corresponding to the arm length change. Since the first detection, LIGO and its partner observatories, Virgo in Europe and Kagra in Japan, have detected dozens of gravitational wave events from merging black holes and neutron stars. Each detection is a direct measurement of the oscillating space-time geometry as gravitational waves pass through the detector. Each detection is a measurement of space-time itself, doing what general relativity predicts: oscillating, rippling, carrying energy, affecting the rate at which time passes. Let us now talk about what the physics of time dilation implies for one of the most speculative but physically motivated ideas in theoretical physics: the concept of time travel to the future. Special and general relativity do not merely predict time dilation as an abstract effect. They establish that any trajectory that maximizes proper time, the time experienced by the traveler, is also the trajectory that appears to have the traveler return to the future. A traveler who moves at high velocity or spends time near a massive object accumulates less proper time than a traveler who remains stationary in flat space-time. When they return, or when they are reunited with the comparison clock, they find themselves in the other clock's future. This is time travel to the future in a completely precise sense. It is not a metaphor, it is not an approximation. A crew that travels at 99.9% of the speed of light for 10 years of their proper time, and then returns, finds themselves in Earth's future by approximately 224 years relative to their departure. They have travelled to the future, the year 224 after their departure, by accumulating only 20 years of their own proper time. This is one-way time travel. Once you arrive in the future, you cannot return to the past by the same mechanism. You can travel further into the future by repeating the process, but you cannot undo the elapsed Earth time. Time travel to the past is an entirely different and far more speculative matter. General relativity does admit mathematical solutions, called closed time-like curves, in which space-time is so curved that a path through space-time can loop back to its starting point in both space and time. A traveller following such a path would return to the same location at the same time they departed. Closed time-like curves appear in specific solutions to Einstein's equations. The Gödel universe, discovered by mathematician Kurt Gödel in 1949. The interior of certain rotating black holes described by the Kerr metric. Solutions involving exotic matter called wormholes. Whether any of these solutions correspond to physical reality rather than mathematical possibilities is unclear. The consensus among physicists is that some physical principle, perhaps related to quantum mechanics, prevents the formation of closed time-like curves in the real universe. Stephen Hawking proposed what he called the chronology protection conjecture, the hypothesis that the laws of physics prevent time travel to the past because such travel would lead to logical paradoxes. The paradoxes of past time travel are familiar from science fiction. The grandfather paradox, in which you travel back in time and prevent your own birth. These paradoxes have been analysed seriously by physicists and have not been satisfactorily resolved within classical general relativity. The resolution likely requires a complete theory of quantum gravity, which we do not yet have. Time travel to the future, through relativistic time dilation, is not speculative. It is confirmed physics. Time travel to the past remains deeply uncertain and is likely prevented by physical principles not yet fully understood. Let us now talk about the practical engineering challenges that relativistic time dilation creates for future space missions, about the specific technical problems that arise when mission timescales become long enough for relativistic effects to matter. For current space missions, the primary timekeeping challenge is the GPS correction we have already discussed, ensuring that clocks aboard satellites and on the ground remain synchronized despite the relativistic effects. This is solved engineering. The corrections are calculated precisely and applied consistently. For interplanetary missions to Mars and beyond, communication delays are already a significant engineering challenge. Light travel time from Earth to Mars varies between about 3 minutes at closest approach and about 22 minutes at farthest. Commands sent from Earth to a Mars spacecraft arrive at the spacecraft minutes to tens of minutes after they were sent. The spacecraft must therefore be designed to operate autonomously for significant periods. It cannot wait for a real-time command in response to every new situation. Relativistic time dilation at interplanetary mission velocities adds milliseconds to seconds of additional timing uncertainty, significant for very precise timing applications, but manageable for most mission operations. For hypothetical missions approaching significant fractions of the speed of light, the engineering challenges multiply dramatically. Communication with Earth becomes increasingly difficult as the Doppler shift redshifts outbound signals and blue shifts inbound signals by large factors. Navigation becomes challenging because the aberration of starlight changes the apparent positions of stars significantly from the traveler's reference frame. Mission planning requires accounting for the fact that time passes differently aboard the spacecraft than on Earth. Mission durations, resource consumption, crew age, and equipment lifetimes must all be calculated in proper time rather than coordinate time. The most significant engineering challenge for genuinely relativistic missions is the propulsion itself. Achieving significant fractions of the speed of light requires energy inputs that dwarf anything in current or foreseeable technology. The kinetic energy of a 1 kilogram mass moving at 90% of the speed of light is approximately 5.9 times 10 to the 16th joules, comparable to the energy released by a several megaton nuclear weapon. Accelerating an entire spacecraft of any practical mass to relativistic velocities represents an energy challenge that has no solution in current physics. This engineering reality means that for the foreseeable future, genuinely significant time dilation, the kind that produces years or decades of asymmetric aging, is the domain of physics and science fiction rather than engineering. The physics is real. The consequences are certain. The technology to experience them is absent. Let us now talk about what time dilation says about the nature of the universe at its deepest level, about the picture of reality that emerges when we take seriously that time is not absolute. The picture is this. The universe is not a three-dimensional space evolving through time. It is a four-dimensional space-time, a static geometric structure in which all events at all times exist simultaneously in the mathematical sense. Different observers moving through this structure experience different slices of it as their present moment. Their subjective experience of time flowing is the experience of tracing a path through this static four-dimensional structure, accumulating proper time as they move. This picture, sometimes called the block universe or eternalism, is the natural interpretation of special relativity taken at face value. It implies that the past, present, and future all exist equally in some sense, that there is no objective distinction between what has happened and what will happen, only a distinction between what lies along the backward light cone and the forward light cone from any given event. Whether this is literally true, whether the future is in some sense already determined, already existing in the geometric structure of space-time, is a question that crosses from physics into metaphysics. Physics describes the geometry of space-time and the rules governing matter and energy within it, but does not directly address questions about the ontological status of past and future events. What is physically certain is this: time is not what Newton thought it was, not an absolute universal flow proceeding identically everywhere at all times. Time is local. It is bound to the observer who experiences it. It depends on the observer's path through space-time, their velocity, their proximity to massive objects, the accumulated history of their trajectory through the four-dimensional structure of the universe. This is one of the most profound revisions in the history of human thought. For millennia, time was assumed to be the universal backdrop against which everything happens, the stage on which the play of the universe performs. Special and general relativity revealed that time is instead part of the play itself, that it bends and stretches and accumulates differently for different actors, depending on how they move through the stage. The stage and the play are the same thing. The experimental confirmation of time dilation, in particle accelerators, in atomic clocks on aeroplanes, in GPS satellites, in the decay rates of cosmic ray muons, in the light curves of distant supernovae, is the confirmation that this picture is not merely elegant mathematics, but accurate physics. Time slows down in space. It slows down near massive objects. It slows down for anything moving at high velocity. Not as a perception, not as an illusion, not as a metaphor, as a fact about the structure of the universe. A fact that was unknown to every human being who ever lived before 1905. A fact that is now incorporated into the engineering of every GPS receiver you have ever used. A fact that is as well confirmed as any fact in the history of science. And a fact whose deepest implications, for the nature of time itself, for what it means to exist as a creature embedded in a four-dimensional space-time, for the relationship between physics and the felt experience of being alive and conscious, remain genuinely and profoundly open. Let us now talk about what happens when time dilation meets the quantum world. About the specific interference between relativistic effects and quantum mechanical behavior that represents one of the most active frontiers in current physics. Quantum mechanics is the framework describing the behavior of matter at the smallest scales: atoms, molecules, fundamental particles. It is inherently probabilistic. It does not predict definite outcomes for individual measurements, but instead gives probability distributions for the possible outcomes. At the heart of quantum mechanics is the superposition principle. A quantum system can exist in a superposition of multiple states simultaneously, with the superposition collapsing to a definite outcome only when a measurement is made. Combining quantum mechanics with special relativity required the development of quantum field theory, a framework in which particles are excitations of underlying quantum fields. Quantum electrodynamics, the quantum field theory of electromagnetism, was developed in the late 1940s and is the most precisely tested theory in the history of physics, with predictions confirmed to better than 1 part in a trillion. But quantum field theory as it stands is developed in flat space-time, the space-time of special relativity, without gravity. Combining it with general relativity, with curved space-time requires quantum gravity, the elusive unified theory. In the absence of quantum gravity, we can make approximate calculations by treating gravity as a classical background and quantum matter as existing in this background. This approach is called quantum field theory in curved space-time. One result of quantum field theory in curved space-time is the Hawking radiation prediction, the theoretical result that black holes should emit thermal radiation due to quantum effects near the event horizon, causing them to slowly evaporate over astronomical timescales. Hawking radiation has not been directly observed. The expected radiation from stellar mass black holes is far too weak to detect, but it is widely accepted as a robust theoretical result. Another result is the Unruh effect, the theoretical prediction that an accelerating observer in a vacuum would see a thermal bath of particles while a stationary observer sees none. This is directly related to time dilation. Acceleration and gravity are equivalent by the equivalence principle, and gravitational time dilation and acceleration are linked. The Unruh temperature seen by an accelerating observer is directly proportional to their acceleration. An observer accelerating at 9.8 meters per second squared, 1 standard gravity, would see a thermal bath at approximately 4 times 10 to the minus 20 Kelvin, far too cold to detect. But at accelerations near the Planck acceleration, the extreme limit, the temperature would be near the Planck temperature, the highest meaningful temperature in physics. The Unruh effect has not been directly observed either. The required accelerations are far beyond anything achievable. But analog experiments in condensed matter physics have observed similar effects in controlled laboratory settings, providing indirect support. More directly relevant to current experiments is the growing field of relativistic quantum information, the study of how quantum information, entanglement, superposition, quantum correlations, behaves in relativistic settings. A key question is what happens to quantum entanglement between two particles when one particle is accelerated or placed in a gravitational field. Does the entanglement survive? Does the time dilation experienced by one particle affect its quantum state in ways that are observable at the other particle? Experiments are beginning to probe these questions at the interface of quantum mechanics and relativity. Satellite-based quantum communication experiments, including the Mitchus satellite launched by China in 2016, have tested quantum entanglement over distances of thousands of kilometers, approaching the scales where relativistic effects become relevant for quantum communication. The interaction between gravity, time dilation, and quantum entanglement is one of the most active research areas in fundamental physics. Let us now talk about what the physics of time dilation means for the search for extraterrestrial intelligence, for the Fermi paradox, and the question of why we have not heard from other civilizations. Relativistic time dilation offers an interesting resolution to one aspect of the Fermi paradox, the question of why no alien civilization has physically colonized the galaxy. If interstellar travel at relativistic velocities involves significant time dilation, then a civilization sending colonists to other star systems is effectively sending those colonists to a future, possibly a very distant future, of the civilization that sent them. Consider a civilization sending a colony ship to a star 100 light-years away at 99% of the speed of light. From the home civilization's perspective, the ship takes approximately 101 years. From the crew's perspective, about 14 years pass. When the crew arrives, they are 14 years older than when they left. But the home civilization has aged 101 years. 2 to 3 generations have lived and died since departure. The colonists arrive as representatives of a civilization that no longer exists in the form that sent them. the home civilization has changed dramatically over the century. The colony, built by people who left 14 years ago subjectively, is culturally tied to a 100-year-old version of a civilization that has moved on. Maintaining coherent interstellar civilization across such temporal discontinuities would be profoundly challenging. At galactic scales, distances of thousands or tens of thousands of light years, the time dilation becomes so extreme that relativistic colonization effectively severs all meaningful cultural and social continuity between the home world and the colony. The colonists would return to find their home civilization unrecognizable, separated by thousands of years rather than the decades of their own experience. This temporal disconnection may be one reason why galaxy-spanning civilizations are rare or absent, even if interstellar travel is physically possible. The practical barriers to maintaining coherent civilization across relativistic time discontinuities may be as significant as the engineering barriers to achieving relativistic velocities. Let us now talk about something rarely discussed in popular treatments of time dilation: its implications for the subjective experience of consciousness and identity. If time passes at different rates for different observers, then the question of personal identity across time becomes interesting in a new way. We normally think of personal identity as continuity of consciousness through time. You are the same person you were yesterday because your consciousness and memory connect your present experience to your past experience through continuous time. For a relativistic traveler, the consciousness and memory connections are intact. They experience continuous time from their subjective perspective, but their relationship to the external world, to other people, to the civilization they came from, to the shared temporal context that grounds social identity, is disrupted by the time dilation. A crew member returning from a relativistic mission who finds that 200 years have passed on Earth is in a position with no precedent in human experience. Their memories and identity are continuous. Their subjective age is decades. But the world that formed their identity, the culture, the relationships, the historical context, is separated from the present by 2 centuries. They are not merely geographically displaced, they are temporally displaced in a way that is physically irreversible. The psychological literature on identity and belonging suggests that the cultural and temporal context is not incidental to identity, but constitutive of it. We understand ourselves in relation to the communities and histories we are part of. To return to a world where that context has been overwritten by 2 centuries of change is to find oneself constitutively homeless, not just without a home, but without the temporal context that makes a home possible. This is the human reality underneath the elegant mathematics. Time dilation is real. Its consequences for people who experience it significantly are not merely numerical, they are existential. The physics of time is among the most beautiful and most confirmed in all of science. The human meaning of that physics, what it would mean to be a person for whom time has passed differently than for everyone you love, is among the most poignant things that physics has ever implied. Let us talk about what time dilation means for the specific question of the biological aging process, about whether the slowing of time in relativistic conditions corresponds to a slowing of biological aging, and what the experimental evidence actually says about this. The answer is yes, and the reason illuminates something profound about the nature of time dilation itself. Biological aging is fundamentally a physical and chemical process. DNA damage accumulates over time. Telomeres, the protective caps at the ends of chromosomes, shorten with each cell division. Proteins misfold and accumulate as cellular cleanup mechanisms become less efficient. Mitochondrial function declines. These processes proceed at rates governed by the laws of chemistry and physics, by the rates of chemical reactions, by the diffusion of molecules, by the quantum mechanical probabilities of electron transfer in enzymatic reactions. All of these rates are determined by the local proper time of the biological system undergoing them. A biochemical reaction that takes 1 second of proper time takes 1 second of proper time regardless of whether that proper second corresponds to 1 external second or 100 external seconds. The chemistry does not know about external coordinate time. It knows only the local proper time of the atoms and molecules undergoing the reactions. Therefore, a person undergoing significant time dilation, travelling at high velocity or residing near a massive object, ages at the rate set by their proper time. If their proper time passes at half the rate of external coordinate time, they age at half the rate as measured by the external clock. When they return and compare their biological age to their compatriots who remain behind, they are genuinely, biologically younger. Not just younger by the clock, but younger in every measurable biological sense. Their cells have divided fewer times. Their telomeres are longer. Their accumulated DNA damage is less. Their mitochondrial function is better preserved. This is not a theoretical prediction awaiting confirmation. It is the direct consequence of the confirmed physics. The muons that survive to sea level are not merely running slow on their internal clock. Their entire physics is running slow by the same factor. Their radioactive decay, which is a quantum mechanical process governed by the proper time of the muon, proceeds at the rate set by their proper time, which is dilated relative to Earth's coordinate time. This is why they survive. For a human being, the biological aging process is more complex than muon decay, but operates according to the same fundamental principle. The proper time governs all local physical and chemical processes. Aging is a local physical process. Therefore, aging slows by the same factor as the proper time. The experimental confirmation of this for biological systems is indirect. We cannot run a relativistic experiment on humans, but it is implied by the confirmed physics of time dilation at the cellular and molecular level. Every biological clock, cell division cycles, circadian rhythms, telomere shortening, would proceed at the proper time rate. Let us now talk about a specific and counterintuitive aspect of time dilation that is often overlooked: the fact that the traveller experiencing time dilation does not perceive the universe around them as moving in fast motion. If an external observer sees the traveller's clock running slow, the traveller aging slowly, you might naively think the traveller sees the external universe running in fast motion. Not quite. The relationship is more subtle and depends on whether you're considering what the traveller sees versus what the traveller calculates. What the traveller sees, the actual light reaching their eyes from distant objects, depends on the Doppler effect as well as time dilation. An observer moving toward a source of light sees it blue-shifted and at a higher apparent frequency. More photons per second arrive at their eyes. An observer moving away sees it red-shifted and at a lower apparent frequency. During the outbound leg of a relativistic journey, the traveller is moving away from Earth and sees Earth time apparently running slowly. Signals from Earth arrive at long intervals. The observed processes on Earth appear slow. During the return leg, the traveller is moving toward Earth and sees Earth time apparently running fast. Signals arrive at short intervals. Processes appear accelerated. When the round trip is complete and you average over both legs, the net effect is that more time has passed on Earth than on the spacecraft. This is the confirmed time dilation asymmetry. But the instantaneous visual experience during each leg is not simply Earth appears fast or Earth appears slow. It is the combined Doppler and time dilation effect that produces these specific visual appearances during each leg. This distinction between what you see and what the physics actually predicts is important for understanding why the twin paradox is not paradoxical. The traveller does not simply see the universe moving in fast motion throughout. The experience is direction dependent and changes during the acceleration phases. Only when the full accounting is done, proper time accumulated along the full trajectory, does the asymmetric aging emerge as a definite prediction. Let us talk now about time dilation in the context of the most energetic particle accelerators ever built, about what experiments at CERN and other accelerators reveal about time dilation at extreme velocities. The Large Hadron Collider at CERN accelerates protons to velocities corresponding to energies of up to 6.5 trillion electron volts per proton. At this energy, the protons are moving at approximately 99.9999991% of the speed of light, a fraction so close to 1 that the Lorentz factor, gamma, is approximately 6,930. Each proton is experiencing time approximately 6,930 times slower than the LHC laboratory frame. The practical consequences for accelerator operations are significant. The proton beams must travel around the 27-kilometer LHC ring many times per second, approximately 11,000 times per second, to reach full energy. The timing of the magnets that bend the beams, the radio frequency cavities that accelerate them, the collimators that clean stray particles, all must account for the relativistic kinematics of particles moving at essentially the speed of light. Many of the particles produced in collisions at the LHC are unstable. They decay after short proper times. At rest in a laboratory, a pion, one of the common collision products, has a proper lifetime of approximately 26 nanoseconds. At LHC energies with gamma of several hundred, a pion travels many meters before decaying. Its proper lifetime of 26 nanoseconds corresponds to microseconds of laboratory time. The detectors surrounding the collision points are designed with this extended laboratory frame lifetime in mind. The particle tracks in the detector must be long enough to be measured before decay occurs. This is time dilation as everyday operational reality in particle physics. Not an exotic correction applied once, but the foundational kinematic framework within which every LHC experiment is designed and interpreted. Let us now talk about what time dilation implies for the very early universe, about the conditions near the Big Bang, when the entire observable universe was compressed into an extraordinarily small volume with extraordinarily high energy density and temperature. In the first fraction of a second after the Big Bang, the universe was in a state of extreme density and temperature. During the first 10 to the minus 43 seconds, the Planck time, the density and temperature was so extreme that our current physics breaks down. We cannot describe this epoch with current theories. Between the Planck time and approximately 10 to the minus 6 seconds, 1 microsecond, the universe was filled with a quark-gluon plasma, a soup of quarks, gluons, electrons, neutrinos, and other particles at temperatures of trillions of degrees. At 1 microsecond after the Big Bang, the temperature had cooled enough for quarks to combine into protons and neutrons. At these early times, the universe was in a state of extreme gravitational energy density, essentially a universe-filling black hole in some sense, and the gravitational time dilation was correspondingly extreme. But because every part of the universe was at the same density, because the universe was spatially homogeneous at large scales, there was no gradient in gravitational potential and no differential time dilation between different regions. Gravitational time dilation requires a gradient, a difference in potential between two locations. In a perfectly homogeneous universe, there is no such gradient. For digital information stored in spacecraft computers, in solid-state drives, in memory chips, in the quantum states of physical systems, the same principle applies. The physical processes underlying information storage and retrieval all proceed at the proper time rate. A stored bit does not decay faster or slower due to time dilation. The physical processes that could corrupt it proceed at the proper time rate of the storage medium. This preservation of information under time dilation is not merely a technical point. It is connected to one of the deepest principles in physics, the conservation of information. The laws of physics, both classical and quantum, do not allow information to be destroyed. Time dilation, a geometric effect of the structure of space-time, does not violate this principle. It changes the rate at which processes unfold, but not the information content of the systems undergoing those processes. A relativistic traveler returns with all their memories intact. A spacecraft's computers retain all stored data. The physical record of what happened is preserved. Only the relationship between that record and external coordinate time has changed. This is the final and perhaps most important thing to understand about time dilation. It does not erase, it does not corrupt, it does not destroy. It stretches. The fabric of experienced time stretched taut against the geometry of space-time. Each second of proper time as full and as real as any other second, carrying all the information of everything that occurred within it. Which brings us back to where we started. Time slows down in space. Not as a metaphor, not as poetry, as a fact about the structure of the universe. A fact confirmed in particle accelerators, in atomic clocks on aeroplanes, in the GPS system you have used today, in the survival of cosmic ray muons reaching sea level, in the time-dilated light curves of supernovae a billion light-years away. A fact that was unknown before 1905. A fact that follows from two deceptively simple observations: that the laws of physics are the same for all observers in uniform motion, and that the speed of light is constant for all of them. From those two observations, forced through the mathematics with complete logical rigor, falls out a universe in which time is not the absolute backdrop Newton assumed, but a local, observer-dependent, geometrically structured feature of a four-dimensional space-time. The GPS satellites above you right now are running their clocks at a slightly different rate than the clocks in your phone. The correction is applied continuously. Without it, the system fails within hours. The physics is not optional. The muons falling through the upper atmosphere right now, millions of them every second, passing through your body without interaction, should, by classical physics, have decayed long before reaching sea level. They have not. They are here because time ran slower for them. They are natural clocks, whose faces you cannot read, but whose survival is the reading. A clock at the top of a mountain runs faster than a clock at its base. A clock on the ocean floor runs slower than a clock in the air above it. The difference between your head and your feet, if you could measure it precisely enough, is real and present right now as you exist in Earth's gravitational field, your head aging infinitesimally faster than your feet. These are not dramatic effects under ordinary circumstances. They become dramatic only at scales of velocity or gravity far beyond everyday experience. Near a black hole's event horizon, where the curvature becomes extreme, a clock appears to stop from a distant observer's perspective. For a traveller moving at 99.9% of the speed of light toward a distant star, 70 days of their proper time corresponds to over 4 years of Earth time. The terrifying reality of why time slows down in space is not that the physics is strange, though it is that the physics is true. That the universe is not structured the way intuition says it is. That there is no universal clock ticking in the background against which all events are measured. That time is not the stage on which the universe performs. It is part of the performance. That what we call time is something local, specific, attached to a particular trajectory through 4-dimensional space-time, shaped by velocity and gravity and the accumulated history of every acceleration and deceleration along the way. And the most terrifying implication of all, not terrifying in a frightening sense, but terrifying in the sense of vertigo before something genuinely vast, is what this means for any being that actually experiences it significantly. A crew travelling at high velocity returns younger than the civilization that sent them. Not metaphorically, biologically. Every cell in their body has divided fewer times. Every telomere is longer. Every accumulated damage is less. They are younger, in every measurable physical sense, than the people who waved goodbye. And those people are gone. Not gone as in moved away, gone as in time has moved past them, years or decades or centuries of it, and the world those travellers knew is separated from the present by an unbridgeable gap of elapsed history. The crew is young. The world is old. The reunion, if there is one, is between two versions of the same civilization, separated not by distance, but by time. And time is the one distance that cannot be closed by returning. This is not science fiction. The physics is confirmed. The engineering to experience it significantly does not exist yet. But the physics is not waiting for the engineering. The universe is already structured this way. It has been structured this way since before there were any beings capable of noticing. Time has been local, observer-dependent, geometrically shaped, from the beginning, throughout the 13.8 billion years of cosmic history, in every corner of the observable universe, whether anyone was there to measure it or not. We discovered this in 1905. We confirmed it continuously for the 120 years since. We built it into the GPS you used to navigate here. We watched it in the survival of particles that should have died before reaching the ground. We measured it in the stretched light curves of exploding stars a billion light-years away. The universe does not owe us intuitive physics. It does not arrange itself for our convenience or our comfort. It is what it is, 4-dimensional, locally temporal, geometrically curved by mass and energy, structured by the invariant speed of light into a causal web that is the same for every observer, regardless of their motion. Within that structure, time flows differently for different observers. Within that structure, aging is local. Within that structure, the question of how much time has passed depends on who you ask. And the answers can differ by seconds, or years, or centuries, or millennia, depending on the path through space-time each observer has travelled. This is the terrifying reality. It is also the beautiful one. The universe is stranger than we assumed. It is more precisely structured than intuition suggested. It follows rules, not our rules, not rules chosen for our comfort, but rules that are consistent and universal, and that have been the same since the beginning. Rules that we have figured out, imperfect beings on a small planet around an ordinary star, through observation and mathematics and the willingness to follow evidence wherever it leads, regardless of how strange the destination. Time slows down in space, and now you know exactly why.